Building on from what you've studied in first year, we're going to look at transformations, but composite. So just to recap on what we did last year, there are three types of transformations that you would have studied. So you've got translations, stretches, and reflections. And I've started with the graph of f of x equals x squared, and we're just going to quickly draw these 6 graphs as a general transformation and what they do. I'm also going to plot each point on the graph where the point 1, 1 was. Okay. So this one here, we're taking the x value and we're adding a to it, which means we are moving in the opposite x direction by a factor of a. So this turning point here is now at a, and what was the point 1 is been moved that way by a, so this is now 1 minus a. Okay, and that still has a y coordinate of 1 because we've only changed stuff in the x direction, nothing has changed in the y direction. So this is translated by minus a 0. This one here, however, doesn't translate it by minus a in the y direction, it actually translates it by a in the y direction. So it's going to move up. This point here is now a, and the point that was 1, 1 is still going to be 1 in the x direction because nothing's changed, but it's now going to be up here at a plus 1. And this is a translation by the vector 0a. So what you may have been taught is that if it affects the x, if it's inside the bracket directly, it does the opposite of what you think. So it actually subtracts a from all the x coordinates. And if it's outside the bracket, doesn't affect x directly, then it does what you think and moves it up. Similar is true then for stretches. So in the y direction, you're going to stretch it up by a scale factor of a. The point 1, 1 is now going to be the point 1a, but the turning point is still at the origin. But again, for the x direction, it's going to squash it in the x direction by a scale factor of a, which is the same as a stretch of 1 over a. So it's still going to look like that. But now the coordinate that was 1, 1 is now going to be 1 over a, 1. And you can see that a transformation in the y direction has only affected the y coordinate, and a transformation in the x direction has only affected the x coordinate. So this is a stretch parallel to the y-axis by a scale factor of a, and this is a stretch parallel to the x-axis, scale factor of 1 over a. So all the x coordinates divide by a rather than times by a. So that's what's going on there. And then the reflections. This is affecting all the y coordinates. So this is actually going to be a reflection in the x-axis because all the y coordinates have jumped down. The x coordinate is unchanged, it's still going to be 1, but this on the y coordinate will be minus 1. So that is a reflection in the x-axis, or in the line y equals 0 if you like. And this one here is actually going to not affect my graph at all in this case because it is a reflection in the y-axis, which is x equals 0. And if you consider the original graph, so the original function f of x, which was defined as x squared, f of minus x therefore is minus x squared, which is just x squared, so it doesn't change in this case, it's a special case. That will always happen if the graph has already got a line of symmetry in the y-axis, which this one does. So that's what you've done in first year, and now looking at second year, how do these transformations interact with one another? So you may have done in first year translations in both x and y, or stretches in both x and y, but what about a translation in x and a stretch in x? What does that look like? So this is the general transformation. F of x maps to a times f of bx plus c plus d. So this has got a stretch in the x, a stretch in the y, a translation in the x, and a translation in the y. So they're all amalgamated into one massive transformation. Now sometimes you might have an a and b that is a 1, so there's no transformation, no stretch transformation, or you may have a c and d that's a 0, so there's no translation transformation. But this just covers the general case. So just like we had over here, when it affects the x, it does what you think, and when it affects the y, when it affects the x, it doesn't do what you think, and when it affects the y, it does what you think. So affecting the x, or the x direction, it does the opposite of what you think. Or the opposite of intuition, I should say. So replacing x with bx plus c, algebraically we would follow BIDMAS, which would mean we would do the multiplication before we do the addition. But because this is affecting the x directly, and it does do the opposite of what we think, or opposite of intuition, then actually it's the translation that happens first, and then the stretch. If you wanted the stretch to happen first, you would need to put brackets around the addition. So this is actually a translation by minus C0, again does the opposite of what you think, so you've added C to all the x values, but it means you translate by minus C, followed by a stretch parallel to the x-axis by a scale factor of 1 over b. Again, does the opposite of what you think. So you've multiplied all the x values by b, which means actually you divide all the x values by b in the transformation. Okay, so it does the complete opposite of what you think. You've added c, you've subtracted c. You've multiplied by b, you divided by b. And you don't follow BIDMAS. You follow, if you like, SAMDIB. And you would get the translation, or the addition, before the multiplication. So the translation occurs before the stretch. And that's important because it matters which we're going to do these transformations, because you'll get different answers. But of course, replacing f of x with a times f of x plus d, this does what you think. So this is a stretch parallel to the y-axis, scale factor a, followed by a translation by the vector 0, d. So this one does what you think. It does the multiplication before it does the addition. It does the multiplication as a multiplication. It's a stretch parallel to the y-axis, scale factor a, when you're timesing by a, and you're adding d, and you actually move up by d. Okay. Let's have a look at a quick example. So back to our original graph that we had a minute ago. F of x is x squared, and we have this transformation here. So this transformation represents all four that we talked about. A stretch in the x is there, a stretch in the y, a translation in the x, and a translation in the y. So just going to break it down step by step. So there's my graph. Point 1, point 1. Okay, so in terms of x then y or y then x doesn't matter, as long as the two transformations in the x direction are followed in this order and the two transformations in the y direction are followed in this order. It doesn't matter how you combine the x and y, because these two directions are perpendicular, they don't affect each other. Okay, they are independent of each other. But within the x and within the y, you must make sure you get them in the right order. So let's do the x first. Let's do the translation by minus c. So the translation in the x is going to be by 1. So the whole thing's going to move to the right by 1. So the point that was 1, 1 is now the point 2, 1. And then you do the stretch in the x direction. So that's going to squash everything in the x direction so that all the x coordinates are halved. So it's going to look like that. The y coordinate is still going to be unchanged. It's still going to be 1. Okay, it's not changed from this because I've only affected the x direction for now. But this x coordinate here, which was a 2, has now been halved to a 1. So what was the point 1, 1 is actually back at the point 1, 1, but the graph looks very different because the turning point is now at a half on the x-axis rather than at the origin. Okay, so there is a change. Now that we've done the two x directions, we can now look at the y directions. So in the y direction, we do the stretch followed by the translation. So let's do the stretch first. So stretch parallel to the y-axis by a scale factor of 2. So all that's going to do, it's going to double all of my y coordinates. The x coordinate is still going to be 1. Okay, that's not going to change now because everything I'm doing now is in the y direction. But that's going to go to a 2 because it's been stretched in the y direction. And then finally, I need to add 4 to all of my y values. So this turning point is going to go up by 4. This point's going to go up by 4. This point's going to go up. Everything's going to go up by 4. Something like that. It's still got an x coordinate of 1, but it's now got a y coordinate of 6 because what was 2 is added 4 to it, and it's now up there at 6. The turning point here, that is going to be at a half 4. Okay, that's the turning point in there. And that's the graph. That's the graph of 2f of 2x minus 1 plus 4, which in this case, because of our definition of f, is equal to 2 into 2x minus 1 squared plus 4. Okay, and that looks like completed square form, which it is. And if you wanted to, you could multiply all the brackets and get to ax squared plus bx plus c if you wanted to. But there's no need. Okay. So in general then, the graph of y equals f of x maps to the graph of y equals a f of bx plus c plus d. We can break that down into 3 transformations followed in this very particular order. First of all, do the stretch parallel to the y-axis by a scale factor of a. And the reason why we do that is because in the y direction we do the stretch first. In the y direction we do the translation second, but in the x direction we do the translation first, so we can then combine the 2 translations together. So you're just translating by the vector minus cd. So that's 2 translations together into 1. And then finally, once you've done the translation in the x direction, you're able to do the stretch in the x direction. So stretch parallel to the x-axis by a scale factor of 1 over b. Just to note, if a or b are negative, then the corresponding stretches will also include a reflection in the x and y-axis respectively. So if a is negative 2, you could reflect in the x-axis and then stretch by 2, or vice versa. If b is negative 5, for example, you would reflect in the y-axis and then stretch by a scale factor of 1 over 5, or vice versa again, doesn't matter for that. All right. Thank you for watching.